Hello, and welcome to this lesson on the key reactions of alcohol. There are a number of reactions we will be looking at today, so let's quickly highlight them. We will begin with the combustion of alcohol. This will flesh out the uses of alcohols as a fuel additive. Next, we will look at the partial oxidation of alcohols. This will allow us to explain why wines go off. Then, we will move on to understanding the dehydration of alcohols. Finally, we'll understand the reactions of alkenes with sodium. So far, we've talked about various alcohols, such as methanol, ethanol, propanol, and butanol, and you've learned about their main uses. Building on this foundation, today's lesson will advance our chemical understanding by examining how these alcohols behave in various reactions, which helps us gain insights into their chemical properties and reactivity. Let's begin with combustion. When alcohols react with oxygen, they undergo a combustion reaction similar to alkanes. The general equation for the complete combustion of an alcohol is alcohol plus oxygen produces carbon dioxide plus water. For example, consider the combustion of methanol. We can start with the word equation methanol plus oxygen produces carbon dioxide plus water. Then, transitioning into formulas, this gives us CH3OH plus O2 produces CO2 plus H2O. Then, finally, we need to balance this equation. Pause the video and have a go at balancing it yourself. If you've gone ahead and done this, you should have the following. 2CH3OH plus 3O2 equals 2CO2 plus 4H2O. Combustion of alcohols is an exothermic process, meaning it releases energy. The energy released during the combustion of alcohols can be harnessed as fuels, which is why methanol, ethanol, propanol, and butanol are often used as biofuels. This energy release makes alcohols useful in various applications, as we have outlined in our previous lesson. Now, let's take a look at partial oxidation. Combustion is an example of complete oxidation, but alcohols can also undergo partial or mild oxidation. To oxidize alcohols, we use specific chemicals known as oxidizing agents. One example of an oxidizing agent for alcohol is potassium dichromate. When alcohols are exposed to air or oxygen in the presence of an oxidizing agent, they undergo controlled partial oxidation and are turned to carboxylic acids, a homologous family that we will explore in detail in upcoming lessons. The oxidation reactions for ethanol, propanol, and butanol can be summarized as follows. Firstly, ethanol plus oxidizing agent equals ethanoic acid. Secondly, propanol plus oxidizing agent becomes propanoic acid. Finally, butanol plus oxidizing agent produces butanoic acid. Don't worry if you're not familiar with the formulae for carboxylic acids. The whole of our next module is dedicated to them, so you'll become comfortable with these formulae soon enough. Despite how these equations are new, you're likely familiar with the process they describe if you've ever witnessed someone describe wine as having gone off. In this reaction, ethanol in wine is gradually oxidized by the oxygen in the air with the help of specific bacteria or an oxidizing agent. This process converts ethanol into ethanoic acid, which is the main component of vinegar. This transformation not only changes the flavor of the wine, but also makes it useful in cooking and preserving food. Unfortunately, it does mean the wine tastes like vinegar. Understanding this reaction helps us appreciate how chemical processes can modify substances in everyday life, turning them into valuable products. Dehydration of alcohols is a chemical reaction where water is removed from an alcohol molecule. This process typically requires heating the alcohol with a catalyst, such as hot aluminium oxide. During dehydration, the alcohol loses a water molecule, resulting in the formation of an alkene. For example, when ethanol undergoes dehydration, it forms ethene. One other important reaction that alcohols undergo is their reaction with carboxylic acids to form esters. We will examine this in upcoming lessons. When an alcohol reacts with sodium, a substitution reaction occurs. In this reaction, the hydrogen atom in the OH group of the alcohol is replaced by a sodium atom. You aren't required to know the details of this reaction for your GCSE exams, but we've decided to include them here all the same. Skip ahead to find out about the observations of this reaction, which is all you need to know for your exams. Stay if you're curious or reckon you might be a budding organic chemist. All right, as we know, alcohols consist of at least one carbon atom bonded to hydrogen atoms and an OH group. Let's ignore everything besides the OH group, since this is what makes the molecule an alcohol. We can symbolize this as ROH, where R stands for the part of the molecule that we're currently ignoring. When this reacts with sodium, the sodium displaces the hydrogen to form a salt with the formula RONA. Writing this out, we have the following equation. Of course, we need to balance this, which gives us this. Let's now give an example of this equation. When ethanol reacts with sodium, we get this equation. In this reaction, ethanol is our alcohol, sodium ethoxide is our salt, and H2 is hydrogen gas. Let's now turn to the appearance of this reaction. When sodium is added to an alcohol, you will see bubbling or fizzing, which is due to the production of hydrogen gas. The alcohol also becomes warm due to the exothermic nature of the reaction. In today's lesson, we explored the various reactions of alcohols, starting with their combustion, where they react with oxygen to produce carbon dioxide and water, releasing energy that makes them valuable as biofuels. We then looked at mild oxidation, where alcohols can be transformed into carboxylic acids using oxidizing agents, exemplified by the conversion of ethanol into ethanoic acid in the production of vinegar. Additionally, we discussed dehydration, where water is removed from alcohols to form alkenes, and we observed the reaction of alcohols with sodium, noting the bubbling due to hydrogen gas production. Understanding these reactions not only highlights the versatility of alcohols in chemical processes, but also their practical applications in everyday life. Watch the rest of the GCSE chemistry course at SoftFOS Education,